Right, here we are again. We've got lesson 5.6, which is on radical expressions and exponents. We're going to be doing a lot of simplifying. And our first question here is, how is an artificial tree like the fourth root of negative 68? And I bet you it has something to do with imaginary roots. Neither has real roots, so they have imaginary roots. Index, rational exponent, those are a couple of things we'll be looking at. And first we're going to discuss the nth root of a. And the way you write that is, the nth root of a is written like so. The root goes up here, like, you know when we have the square root, that's the one we already know, like the square root of 4. There's really a 2 here. We don't write it, but it's understood. So if you want to do the cube root of 8, we have already worked with that too, haven't we? Cube root of 8, you'd write it like this. And you ask yourself what number times itself 3 times would equal 8, and that would be 2. So those are some things that you are already familiar with. The n is called the index number. And the a is called the radicand. Also, the nth root of a can be written as a to the 1 over n. Like for instance, if you're trying to find the cube root of 8, you can write that as 8 to the 1/3. And that's how I prefer to key it into my calculator. When I key it in, I do 8 raised to parenthesis 1 divided by 3. Your 1/3 has to be in parentheses when you put it in your calculator. Under the math button, there is a cube root button under there that you can use if you like, but I prefer this. Also, there's more here. I am going to have to clear off some space here. Let's just clear all the annotations. All right. There are some cases, 4 cases, and roots. The first case is if there is an odd n. So again, we've got, so like the cube root, for instance. If you take the cube root of a number, it doesn't matter if you take the cube root of an odd or a negative, you will only get 1 root. Like the cube root, we could even do negative 8. The cube root of negative 8 is negative 2. There's only one number you can multiply by itself 3 times to get negative 8. So actually I should have said there's one real root. Negative 2 is a real number. If you have an even n, you can actually get 2 real roots. Oh, even n, sorry, I'm getting a little ahead of myself. And a positive radicand. I should do examples over here. So let's do an even root. How about the fourth root of a positive number? Let's do 16. So what number times itself 4 times will equal 16? That's 2. So, oh wait, actually it's plus or minus. Because what if you did negative 2 times itself 4 times? You would also get 16. So I almost forgot it. There's actually 2, plus or minus 2. So that means there are 2 real roots possible. And then if you have an even n and a negative radicand, so let's do the same root, fourth root of negative 16. What number would you multiply by itself 4 times to get a negative? That's impossible. There are no real roots on that one. So no real roots. And if the radicand is 0, if you take any root, fourth, whatever, of 0, you're going to get 0. So there's one root, one real root on that one, and it's 0. So those are the cases that we're going to use here on this next slide. It says find all the real roots. So the fourth roots of 81, when you do that, you can write it like this. And you have to ask yourself, what number times itself 4 times would give you 81? And that would be 3, because 3 times 3 is 9, times 3 is 27, times 3 is 81. But you have to have plus or minus 3, because you could also do negative, 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 negative. And that would also give you positive 81. So this one can be somewhat tricky if you forget. It's kind of like when you take the square root, you need to remember there's plus or minus. Oh, by the way, if it asks for the principal root is just the positive one. So if you forget your plus or minus, you're finding the principal root. Or if it asks you specifically for the principal root, you just give the positive root. All right, this next one, the cube root of negative 125. That's only going to be one number, and it's negative 5. And then the last one, the sixth roots of negative 729. I can't multiply a number an even number of times and get a negative, so this one has no real roots. Try these on your own, and then I will reveal the answers for you. This first one is going to be no real roots. The sixth roots of 1 is plus or minus 1, and the cube root of 125 is 5. Okay, on this chart, the most important part is right here. If you have the nth root of a product, you can break it apart into a product of these individual ones. And then down here, if you have the nth root of a, a quotient, then you can break it apart into these two. And then they've got some examples here to show you. Simplify each expression, assume that all variables are positive. So, on this one you can see we've got two parts. So I'm going to break it apart into two using that product property we just saw on the other slide. And then the cube root of 27 is 3. And the cube root of x to the 6th. You can either think about it, like what would you'd have to do, well here, let me just show you the way I would do it. What I do is I bring along my x to the 6th. And then remember earlier I said that the nth root of a number is a to the 1 over n? That's what I would do here. I would put this in parentheses and raise it to the 1/3. Bring down the 3. And then this property, we already know, a power to a power, you multiply them. So you get 6 over 1 times 1 over 3, which is 6/3, which is 2. I'll show the math though. 6/3, that's the same as 3 times x squared. The book does it another way, but you know, this way I think is just faster, and hopefully it's intuitive and makes sense. On this one, we're going to break it apart as well. You could probably already see what that equals, or simplifies to. The cube root of x cubed is simply x, because you're asking yourself what times itself 3 times will give you x cubed, and that's x. And then we're over this. Now recall that we cannot have a radical in the denominator. And normally when we had radicals in the denominator, like something simple like 1 over root 2, we got rid of that radical by rationalizing and multiplying top and bottom by root 2. Well, over here, and notice too, this is the square root, and we had a pair of them. Here, because it's a cube root, we need 3 of them total, which means I had to multiply 2 of these. So I have to multiply also 2 of them to the top, getting that. And then on top, I'm going to have x. This, because these are both under the cubes, I can put them under one cube and do 7 times 7 is 49. All over, and then the cube root of 3 of these is going to be just simply 7. And so that's the simplified final answer on that one. And be careful too that this 3, make sure it's over here next to the radical and not over here to where you might think it's x cubed. So just be real careful when you write these. These are, I believe, on your own, so try all 3 of these on your own and then I will supply the answers. Oh, I got to talk about this first one though. It's tricky. So you do this. 4 through to 16, we've already done today, is 2. And then this might appear to just be x. However, it is really not. It is really the absolute value of x. And the reason is, say I had this, what I had started with, Let x equal -1. So I plug -1 in, raise it to the fourth, and then take the fourth root. Well, what's -1 to the fourth? Because we start inside first. That's 1. And then the fourth root of 1 is 1. Well, I put in -1 and I got out 1. That means that I'm not getting out x, I'm getting out the absolute value of x right here, because x was -1, and then when I simplified it, I got x equals +1. +1 is the absolute value of -1. So if you just write 2x, that's actually incorrect. And I believe our book wrote 2x, and they're wrong. It needs to be 2 times the absolute value of x. So that one's a super tricky one, and try to remember that. It shows up ever so often. Okay, this one, x to the 8th. I like to write it like this. To start with, I'm going through these kind of quickly, oops, so as not to spend too much of your time here. And then you're going to get, that's 8/4, which is 2. And then down here, we need 4 of these total. So I need to do 3 of them on top and bottom. Ugh. Look at me, I'm going backwards. That's a 4 and that's a 3, and I'm trying to go too fast. So this x is squared. Make sure that 2's over with the x. And this is going to be the fourth root of 3 times 3 times 3, which is 27, all over 3, because the fourth root with 4 of these is going to cancel out to just 3. So there's that one. And then this one's going to be the cube root of x to the 9th. That's the same as x to the 9th to the 1/3. And that's x cubed. This slide I've already talked about, this property right here. But, however, I have not talked about this property. If you have something, here I'll do it with numbers because it's more interesting that way. Say you have 8 to the 2/3. You can write that as 8 squared, the 2 here is the squared, to the 1/3. So I'm breaking apart 2/3 into 2 times 1/3. I can write it this way, or I could do it in the other order. I could say 8 to the 1/3, all of that squared. So that's what this property is saying. However, instead of writing it in exponent form, they're writing it in radical form. Because this would be the same as the square root of 8 to the 1/3, and this is the square root of 8 to the 1/3. So you can see these things here. In this section, there's a lot of manipulating and writing things in different forms and trying to simplify them. So here's an example of using this. We want to write it in radical form and then simplify it. It's almost always easier and faster to take the cube root first, take the root first. So to write it as -125 to the 1/3 squared. So I broke the 2/3 apart into 2 times 1/3. And I want the root inside. And the reason is I'm going to get a smaller number if I do it that way. What's the cube? Okay, and they wanted it in radical form. So I'm going to switch this into radical form, because that's what the book is asking for. See, once I have it in exponent form, I can put it into radical. If you're comfortable going from this form straight to here, that's fine. I just find it might be helpful to go this way first and then down. The cube root of -125 is -5, and then we're going to square that, and we get 25 as our answer. If you do it the other way and do -125 squared and then cube rooted, -125 squared is a really big number, and it would be hard to do that in your head, and it would also be hard to take the cube root in your head. But notice when I did it this way, I was able to do it all without a calculator. Try these on your own. Okay, now I'll do the answers. This is the cube root of 64, which is 4 times 4 is 16, 16 times 4 is 64. So that means that's 4. And it doesn't have a plus or minus out front, so we can just write it, the principal root of 4. This one's going to be 4 to the 1/2 to the 5th. That's the square root of 4 to the 5th. That's 2 to the 5th. That's 32. This one, we want to do the root first, 65 to the 1/4, all of that cubed. Now normally I wouldn't go and do this radical step. I would just go right from here to here. But because it's asking radical form, I'm going to go ahead and do that additional step, like so. The fourth root, oh, that's 625. The fourth root of 625 is 25, I do believe, because 25 times 25, oh, no. It's 5. Because 5 times 5 is 25, times 5 is 125. 125 times 5 would be 625. So that's 5 to the 3rd, which is 125. Whoop. Next. Write each expression by using rational. Oh, I love rational exponents. As you can see, I've been using them all along. So I've got 7 to the 3rd, all of that to the 1/4. And then we want to simplify it by simply multiplying these together, so that's 7 to the 3/4. These ones are fun. 11 to the 6th, all of that to the 1/3. Multiply 6 times a 3rd and you get squared. 11 squared is 121. Okay, do these on your own. Now I'll give the answers. So that's going to be 3 to the 3rd, which is 27. This one's going to be 10 to the 9th to the 1/3, which is 10 to the 3rd, which is 1,000. This one is 5 squared to the 1/4, which is 5 to the 1/2, which we don't know that. That's the square root of 5, so we don't know what that is off the top of our head. So you could just leave it like that. This is an exact answer. Next, we have these properties. Right here, I could write them down, but here they are for you. We've used these already. If you don't remember them, write them down and commit them to memory. Now we're going to use those properties to simplify. So here we are multiplying. We have the same bases. That means we're going to add our exponents. 3/2 plus 3/5 plus 2/5 is 5/5, which is 1. So the answer is 25. This one we're going to be subtracting. So we're going to have 8 to the 1/3 minus 2/3. 1/3 minus 2/3 is negative 1/3. And then remember, because it's a negative exponent, we have to move it down to the denominator and make it a positive exponent. Furthermore, we can actually find the cube root of 8, because 8 to the 1/3 means the cube root of 8, so that's 1/2. Hopefully I'm not going too fast. If I am, you can always be pausing, right? Because I'm just ripping through this. Okay, do these on your own, and then I'll supply the answers. So this one's going to end up being 36 to the 4/8, which is the square root of 36, which is 6. This one's going to be, I would write this as 1/-8 to the positive 1/3. So I'm simplifying the negative exponent first, putting that -8 down here in parentheses. I can take the cube root of -8, it's -2, and so I get -1/2. Here I'm going to be subtracting. 9/4 minus 1/4 is 8/4. 8/4 is the same as 2. 5 squared is 25. I make it look easy, don't I? And that leads us to our almost our last problem here. This is the music one. I am not real good at music, but maybe some of you are. Frets are small metal bars positioned across the neck of a guitar so that the guitar can produce the notes of a specific scale. See, I don't even know what a scale is. To find the distance a fret should be placed from the bridge, I think the bridge is this thingy, multiply the length of the string by this 2 to the blah, blah, blah. So you're going to have the distance equals the length of the string times 2 to the -n/12. They didn't come right out and write that for us, but I'm translating it into that. N is the number of notes higher than the string's root note. Where should a fret be placed to produce a G note on an E string? Now, it's a good thing they told us that that's 3 notes higher, because I would have had no clue whatsoever. We are trying to find distance. Where should a fret be placed? So we're trying to find D. Do we know L? Well, it doesn't say in the problem, but it does say over here in the picture. It shows the length of the string is 64 times 2. And they do tell us the notes is 3 notes higher, thankfully. Otherwise, I would be clueless. We've got 64 times 2 to the negative 1/4. I've tried to understand music, but I'm tone deaf and it just doesn't make sense to me. I love it though. I love music. Okay, what I'm going to do here, I cannot multiply or combine these because the 2 is being raised to a power, the 64 is not. So I'm going to bring the 64 along. I'm going to rewrite my 2 as 1/2 to the positive 1/4. And you know what? I don't know the 4th root of 2. It's a decimal. So I have to bring out my calculator, which I have not used yet today, so I have to pull it up here. Which is good, because then we can practice entering these in our calculator. Okay, come down. And we've got, I'm just going to type it all in. 64. Now 64 times 1/2 to the 1/4 is the same as 64 divided by 2 to the 1/4. So I'm going to key it in that way. 64 divided by 2 raised to. Now, the 1/4 has to be in parentheses. If it is not, you will get the wrong answer. So this 2 raised to the 1/4, that's all one thing. The calculator knows that. And we get 53.8. I don't remember how many units, or decimal places. I'm just going to go to tenths. 53.8. This is a distance, so it's probably in centimeters. And that's that. Let's see what we got on the next page. I was just kind of making sure it made sense. It's a good thing. It's smaller than 64 centimeters. If it was greater than that, I would be worried. And we'll probably, I wonder, I have these on here for some reason. Oh yeah, I remember these came up in the homework. Tell you what, these will be good to do in class together. So let's do those together in class. And that's the lesson quiz, which will be the homework, or that'll be one of the warm-ups. Of course, I hardly want to pass a problem without doing it. I think I'll wait though and let you guys do that in class. So anyway, I'm going to stop now. We'll see you later.